here is the first of the Mathcad sheets. So this is fixing design to AS NZS4600. We're looking at first at bolted connections to clause 5.3. So we're looking at an M10 grade 4.6 bolt in grade 300 steel to a steel angle. Now the two grades are slightly different. We start with putting in our basic parameters. So here is the diameter of the fixing, the spacing of the fixings, the end edge distance of the connected part. Here is the thicknesses of the top sheet and the bottom sheet, and then the strengths, yield strength and ultimate strengths for the top and bottom sheets. A quick check on the minimum edge distance and minimum spacing from clause 5.3.1. We then look at tear out, and each of these sections has a different capacity reduction factor, which you'll find under each of the clauses. And from that, we have a nominal shear capacity, and then we apply our reduction factor to give us a 4.21 on minimum. Then we look at the section tension of the connected part. So that's a little bit of metal between your fixings that has been put into tension because of the action of the fixings. Bear in mind that your fixings are there to transfer your load from one component to another, and you have to follow the whole load path to find what the capacity is of that fixing. So the equation here is given in equation 5.3.3, and we have quite a large capacity in that little bit of metal still left between the holes. Then we look at bearing capacity in clause 5.4.2. Again, we've got our own capacity reduction factor for this section. We put in a nested if, depending on the ratio between the fixing diameter and the thickness of the material. So the C1 is the C parameter for the top sheet, and the C2 is the C parameter for the bottom sheet. So you get different values because of the thicknesses. So then you get a nominal bearing capacity of the two sheets, and then you take the smallest one and apply your capacity reduction factor. Now we look at the bolt hole deformation, and this is given by the equation in 5.3.4.3. We take the minimum of the bearing capacity of the top sheet and the bottom sheet and apply our bearing capacity reduction factor. Then we look at bolts in shear. This is probably not the critical element, because what you'll find in fixings in light gauge steel and in aluminium is that it's not the bolt or the screw or the rivet that is the critical component. It is nearly always the metal that you're joining. And so we just take the gross the section area of the bolt and then apply it. So we make up whether it's going to be within the threads or outside of the threads, and add shear planes and the values together to give us our bolt capacity, which is much higher than the bearing capacity or the shear capacity of the material we're joining. Similarly with the bolts in tension, you've seen this sort of thing before, tension area multiplied by your tensile strength with a capacity reduction factor. Again, much higher than the tensile capacity of the material you're looking at. You can combine the two, and the clause in the code allows you a utilization ratio of combined tension and shear of up to 1.1. Now we look at screws, and that's dealt with in clause 5.4. In this case, we're looking at 14 gauge tech screws. Same material, we're looking at steel sheet and a steel angle. So we pull down our values from those components from above. My convention is, if we're repeating an old value, we put it in grey. If it's a new value, we put it in yellow. It's entirely my creation. You can have your own convention if you like. So we're looking at, first of all, a check on the minimum edge distance and the minimum spacing. And we look at the tension in the connected part again, as we've done for the bolts. And then we look at tilting and hole bearing. And again, we've got that nested if statement to derive the C1, C2 values. And then there's another fancy equation to define what the bearing capacity is. Now, it gives you different equations depending on the ratio of the thicknesses. So if it's less than 1, this is your equation. If it's more than 2.5, this is your equation. Now, what if it's somewhere in between, like we've got? Then you use linear interpolation to derive the actual value. Then you check on the tear out of the shear as limited by the end distance. So we've deliberately put in a small value for our end distance, but we're still having a reasonably large value of your tear out capacity of the material. So that's not going to be the governing factor. Looking at the screws in tension, again, a check on the edge distance. And we're looking at pull out and pull over in clause 4.3.2. And there's a number of different arrangements that they show within this clause. I've just taken a snapshot of one of them. And again, we look at our screw diameter and put in what our washer thickness is and our washer diameter. From that, you get your effective pull over diameter, D-W. And then from that, you get the pull over capacity, what I've called N-ov, and then the pull out capacity, N-O-U. And you'll see in this case that your pull out capacity is the governing factor. Apply our strength reduction factor to that, and you get a value of 1.48. If you're using a top hat, AS NZS4600 has a special clause just for that. And there's obviously some concern about fixing thin top hat sections, which are usually girts or even purlins for light gauge steel structures. And you pull it out and you've got different equations depending on the material thickness and the material grades as well. If you're looking at the connections combined shear and pull over, there's a utilization ratio factor for that. Again, the clause allows you up to 1.1. However, this is only valid if these conditions are met, and in our case, those conditions weren't met. Look at the connection subject to combined shear and pull out, and again, we've got another equation to put it together, and you're allowed up to 1.15 in a combined shear and pull out. In this case, it is valid because our parameters match the conditions given in the code. Just a quick check on the screws themselves. Normally, again, the screw isn't the weak link in itself. So you can look up in tables what the shear capacity and the tension capacity is. In our case, we've said it's 5 kilonewtons. If we're applying 3 in both shear and tension, we put it together and get a utilization ratio of 1.2. That's okay because the clause in the code allows us a utilization up to 1.3. Moving on to rivets, that's dealt with in clause 6 of the code. And we've picked out a 4.8 millimeter blind rivet, which is quite typical in this application. So we put in our parameters for the rivet diameter and the spacing of the rivets. Again, we're looking at top thickness and the bottom thickness. And we put in the strengths, tensile strengths of the two materials. Start with a check on the spacing, then check the tension in the connected part. Look at tilting, hold bearing. Again, we've got two different ways of working out what the design bearing capacity is, depending on the ratio of the thicknesses. Now, in our case, our T2 over T1 is less than 1, so therefore it's going to be the 0.62. Just check if you're going to be limited by edge distance. In our case, we're not. And then we get a final capacity of our rivets in shear. This final one is just to check that you're not exceeding the capacity of the rivet itself. And there are published tables of the shear and axial tensile capacity of, in this case, blind rivets in either steel or aluminium. Leave a like and leave a comment and subscribe to the channel. I see from the analytics that my second biggest audience is in Hong Kong. So welcome if you're watching in Hong Kong. If you have any comments, just put in the comment section under the YouTube video as well.